All right, let's dive right into this explainer. It's kind of funny. The smarter our AI models get, the more they seem to struggle with basic reading comprehension when you hand them a really long document. Today, we're unpacking a massive gap in modern AI, the difference between dumping a giant library of information onto a model and that model actually knowing how to use that information effectively.
Think about it like this. Imagine someone hands you a dense, 1,000-page legal contract, forces you to speed read the whole thing, takes it away, and then demands you answer a hyper-specific question about a single clause on page 402 in one breath. Sounds like a nightmare, right? Well, that's exactly the long context dilemma that today's large language models are facing. They are handed enormous walls of text and expected to process it all and generate a perfect answer on the very first try.
Now, looking at this conceptual breakdown on screen, you can see exactly where things go wrong. It's the critical gap between context access and context harnessing. We've been throwing bigger and bigger memory windows at these models, some up to 128,000 tokens, which is basically an entire novel. But as the visual shows, just having that text in the model's memory doesn't mean the AI can actually use it. The evidence is sitting right there in the input, but the model either hallucinates an answer or completely misses the clue. Access literally does not equal understanding when the sheer volume of noise drowns out the signal.
And just how bad is that noise? Take a look at this chart mapping out token relevance. The curve you're seeing here is wildly steep. Researchers tracked how relevant specific tokens actually are to answering a user's prompt, and for powerhouse models like Qwen and Llama, the top 0.1% of tokens are doing almost all the heavy lifting. We're talking 50 to 80% of the required information packed into a microscopic fraction of the text. To put that in perspective, out of a 128,000 token prompt, a mere 128 words hold the actual answer. The AI is looking for a needle in a digital haystack, and the needle is practically invisible.
So, how do we fix it? Enter a totally brilliant framework called RECONTEXT. In standard or vanilla prompting, the AI just tries to swallow the whole ocean of text and spit out an answer in one go. RECONTEXT flips the script completely. It gives the AI a digital scratchpad. Instead of trying to memorize a chaotic crime scene in one glance, it's like a detective keeping the entire case file open on the desk, but actively jotting down the absolute best clues on a notepad right next to them.
Section 1. The Evidence Pipeline. How RECONTEXT thinks.
So how does this digital detective work actually happen? The RECONTEXT pipeline breaks down into 4 really elegant steps. First, an LLM inference pass. Then, evidence sifting, followed by materialization, and finally, a recursive replay. Let's walk through exactly how this dynamic scratchpad organizes all that data without throwing anything away. Starting with step 1, which is visualized here, the frozen parameter LLM inference. What's crucial to understand about this diagram is that the core model itself isn't changing. The system reads the massive original prompt using frozen parameters. In AI terms, that means we aren't doing any expensive retraining or fine-tuning under the hood. The RECONTEXT framework just wraps around the existing model, utilizing it exactly as it already is, which saves a massive amount of time and computing power.
Moving to step 2, we see the question-conditioned queue-to-context relevance process. Basically, RECONTEXT turns into a magnifying glass. When the model reaches the user's question at the very end of the prompt, the system taps into the AI's own internal attention signals. It looks backwards and essentially asks, hey, based on this specific question, which exact words in that giant document just lit up in your neural network? It's using the AI's internal mathematical heat map to sift through the noise and scout out the highest scoring, most relevant tokens.
But here's the catch, and this is exactly what step 3, evidence materialization, solves. Those individual high-scoring tokens are usually just useless fragments. Maybe it's half a word or a random date. On its own, a scattered token doesn't give the AI enough context. So as you can see in this step, RECONTEXT maps those isolated hits back to their original, full sentences within the document. It physically materializes them, turning a fragmented puzzle piece into a fully grounded, highly readable text span that actually makes sense.
Then we hit step 4, which is the secret sauce, recursive replay. The system takes those newly materialized sentences and feeds them right back into the prompt as a scaffold, positioning them right next to the user's question. Now that the AI is explicitly staring at those concrete clues, its internal state shifts. It has better context. So it runs the loop again. It uses those initial clues to hunt down even deeper, more connected pieces of evidence that it completely missed the first time around.
When we zoom out and look at the overarching RECONTEXT pipeline diagram, the whole genius of the workflow really pops.
Notice how the AI safely holds that massive original context in its memory cache the entire time. It's not deleting anything. But concurrently, it's actively building and refining this explicit evidence pool right next to the user's question. It literally replays the best evidence to itself right before it generates the final answer. It's organizing its thoughts perfectly without ever losing sight of the big picture.
If you want to get theoretical for a second, researchers explain this through the lens of associative memory. Think of the massive document as a passive memory store, and the user's question as a retrieval queue. Explicitly replaying those evidence sentences acts as trace reactivation. From a mathematical standpoint, every time the system loops and replays that evidence, the model's hidden representation is physically moving closer and closer to the exact right answer.
All right, let's move on to Section 2, Proof in the Performance, and look at some real-world benchmarks.
Let's look at how this plays out in a real-world scenario, specifically looking at the Enron scandal example in this figure. The AI was given a massive document and asked, LJM was one of what type of company Andrew Fastow used in the Enron scandal. Now, a standard AI completely chokes on this because it requires multi-hop reasoning across a huge text. But RECONTEXT, it scans the text, materializes 3 highly specific sentences detailing Fastow's complicated web of off-balance sheet entities, replays those sentences in its scratchpad and perfectly nails the answer, independent ghost entities. It connected the dots flawlessly.
And here is the real aha moment. It absolutely crushes AI hallucinations. In another example shown here, the model is asked, who plays the scary nun in The Conjuring 2? A standard model gets lost in the dense text, gets confused by other actors, and completely hallucinates the name Taisa. But RECONTEXT digs in, surfaces the exact quote from the text stating that Bonnie Aarons plays the demon nun, and puts it in the evidence pool. Because that explicit, hard evidence is right there in front of its digital face, it overrides the hallucinated garbage and correctly answers Bonnie. That is the power of grounded generation.
Of course, 1 or 2 cool examples don't prove a theory. The researchers rigorously stress-tested this framework across 8 incredibly diverse datasets, pushing the models to their absolute limit with massive 128,000 token contexts. We're talking natural questions, trivia QA, hotpot QA, narrative QA, you name it. They threw factual QA, complex multi-hop reasoning, and tough claim verification at this thing just to see if it would break.
And the results? Utterly dominant. Just look at this performance table. Across 3 major backbone models, Qwen 3.4b, Qwen 3.8b, and Llama 3.8b, RECONTEXT secured the absolute best average rank across the board. You can see the vanilla accuracy scores on the left and the RECONTEXT boosted scores right next to them. It consistently beat out other advanced baselines that try to compress the prompt or artificially sharpen the AI's attention. It turns out, simply preserving the full text while explicitly organizing the best clues wins out every single time.
If you want the ultimate takeaway number, here it is, 24.6%. By averaging the accuracy across all those brutal datasets, RECONTEXT delivered a massive 24.6% relative gain in mean accuracy over the standard baseline models. That is a quarter of an improvement in overall performance just by giving the AI a scratchpad. It proves beyond a shadow of a doubt that organizing the evidence you already have is just as critical as reading it in the first place.
Now let's look at the internal mechanics on these 2 charts. When the researchers tweaked the dials, they found 2 really interesting thresholds. On the left chart, you can see that accuracy generally peaks at around 2 to 4 recursive rounds of evidence gathering. After that, you hit diminishing returns. Then, looking at the right chart, we see that the optimal token budget, meaning how many clues the AI pulls per round, varies wildly depending on the task. The beautiful thing is that the system automatically adapts, whether it's hunting for a single sharp fact or needing a broad, wide net of contextual clues.
What really makes RECONTEXT a universal game changer is its robustness. Even if you turn on the AI's explicit internal reasoning, what we often call thinking-enabled, RECONTEXT still stacks a 16.7% accuracy gain right on top of it. And it scales down perfectly, too. If you limit the context to a shorter 64,000 tokens, RECONTEXT dominates with a huge 35% relative gain. It's incredibly versatile.
Now, I know what you might be thinking. Surely all this looping and replaying totally destroys the AI's speed and memory, right? Well, looking at this efficiency breakdown, you'll see why that's not the case. Because RECONTEXT only adds a maximum of 128 tokens to the prompt during the evidence replay, it just reuses the massive text that's already sitting in the system's key value memory cache. The result? It adds almost 0 memory overhead to the GPU. It is remarkably lightweight.
And as for time, check out this runtime comparison chart. Yes, the extra read and replay steps do make it slightly slower than a standard vanilla run, clocking in at about 95 minutes on these specific benchmark tests compared to the standard 75 minutes. But look at the alternative. It is drastically faster than other invasive methods like Disco, which force changes to the core decoding logic and drag the runtime out to 200 minutes. Recontextual strikes an incredibly practical balance between high-end performance and real-world efficiency.
Ultimately, the architecture visualized here signals a massive paradigm shift in how we handle data in AI. It proves that we don't necessarily need infinitely larger million-token context windows to make our models smarter. We just need to give them a dynamic scaffold, a smart way to bookmark, organize, and prioritize the clues they've already been given right there in the moment. Which leaves us with a truly fascinating thought to end on. If implementing a relatively simple digital scratchpad can boost an AI's accuracy by nearly 25% today, without any retraining whatsoever, what boundaries are we going to shatter when future models learn to build these recursive evidence pools completely autonomously? It's a thrilling frontier for sure. Thanks for exploring it with us in this explainer.